Good morning, everybody. Today, we're going to be wrapping up our discussion on gas-liquid systems and investigating multi-component material balances with gas and liquids, vapor, liquid is in equilibrium. We're going to work on I think we can do a couple examples today and then probably get into looking at solid liquid and liquid liquid equilibrium systems, which we can wrap up most likely tomorrow. So, recalling from our discussions yesterday, when we were looking at vapor liquid equilibrium involving multiple component systems or multi-component systems, we had a couple expressions to fall back on, looking at Raoult's law and Henry's law. And these expressions were similar, but we applied them to different systems depending on the nature of the mixture under investigation. So when we were looking at Raoult's law, we had stated the partial pressure of our species in the system was equal to the mole fraction in the vapor phase times the total pressure, which was equated to the mole fraction in the liquid phase times the vapor pressure of our species at a specified temperature. Henry's law is similar, but in lieu of a partial pressure, we were interested in a Henry's law constant value at the temperature of interest. And we had stated that Raoult's law was when we had high concentrations of our component, and Henry's law was when we were looking at dilute solutions. So this is rich solutions of I, and Henry's law was for dilute solutions of I. And so use of Raoult's law and Henry's law allows us to estimate the component mole fractions of species in equilibrium with a liquid phase and or a vapor phase and vice versa. So let's look at an example applying some of this information in terms of considering multi-component systems. So if I have a gas mixture consisting of 15% benzene, 10 mole percent toluene, and 75 mole percent nitrogen. And it's at 80 degrees Celsius. Now, if I compress this gas, at that temperature, or isothermally, eventually we will reach the dew point pressure. which the dew point pressure is similar to the dew point we've discussed previously, but it's the pressure in which the first droplet of liquid forms in this gas if it's compressed isothermally. So if we compress this mixture, eventually we'll reach the dew point pressure of the mixture. The question is, at what pressure will this occur? Or simply, what is the dew point pressure of the mixture? Well, to calculate the dew point pressure of a mixture, we can rely on an equation within the text, which states the dew point pressure simply 1 divided by the mole fraction of a component over the vapor pressure of that component at our temperature of interest, plus the mole fraction of our second component times its vapor pressure over its vapor pressure, the mole fraction of our third component times its vapor pressure. So we need the mole fractions of benzene, toluene, and nitrogen, which we have, but we also need the vapor pressures of each of these components at 80 degrees Celsius. And so we know, let's looking at benzene, the mole fraction we said was 15 mole percent, or 0.15. We need to calculate the vapor pressure. Well, we can do that using the Antoine's equation from our table B4 in the text. So for benzene, I have log of P star, keeping in mind it's in millimeters per mercury, A minus B over T plus C, where for benzene, A is approximately 6.89272. B is 531. I'm being a little dyslexic today. And C is 219.88. And so to find the vapor pressure, I plug in these values, 6.89272 minus 1203.531 over the temperature, which was 80 degrees Celsius. So what do I get for P star?
I got 757.
All right, 757 millimeters of mercury. It is. So now we have to look at toluene, which I believe was 10 mole percent. And for toluene, the constants are 6.95805